So, hello again everybody, and today we will discuss some more practical aspects of actually calculating spectrums for real signals. Because so far we have discussed, okay, we have Fourier transform, we can even have discrete Fourier transform or fast Fourier transform, and if we have some signal, we can calculate the spectrum. But the question is, in reality, our signals are of certain time duration. Some of them are very short, some of them are very long. So we have to somehow organize this procedure, and not only that, but also signals do change. That's not like something constant, like a signal, yes? So if we speak about some, I don't know, speech data, for example, then we can clearly see that the signal is kind of on pause, then some burst happening, then again something so like that, then again larger burst, and so forth, yes? So the signal itself is actually non-stationary, non-constant, and changing. And how are we supposed to calculate spectrum of that? That is one of the questions we are going to cover today, because it's nice to have theoretical estimates of spectrums. However, in the reality, we need to consider limited duration of the signal. We need to consider, well, kind of resolution problems that we may have, yes, which I will discuss, and many other things, as well as some undesired effects which can kind of ruin your spectrum picture, yes. So that all is discussed today, and we will go to computer class to do some practical exercise on and electroencephalogram signals, yes, of brain activity, to try and see some processes happening, yes. So basically that's what we are going to do in practical exercise today. But before that, let's go through the lecture part. Well, first of all, what kind of tasks do we want to do in practice, yes? Some things like frequency identification. Say we want to find specific frequency component in the signal to verify that something is happening, yes? Be that, for example, 50 Hertz of the electric circuit, electric power grid, yes? Or 400 Hertz or something else, yes? Another aspect is reading some information, signal recognition, like, fingerprints recognition, voice recognition, all that kind of system also kind of works with the spectrum. Finally, of course, filtering, be that noise filtering or some more advanced stuff like I was showing you in the last lecture. We could take an image and then do some blurring, sharpening, and many other things. That is also filtering of two-dimensional arrays. In particular, very important and very useful is ability to clean some data from the noise. Yes, that is noise filtering, which we will also try to do in practical exercise as well. Not today, but next time. Then detection of specific sudden events happening. Yes, so that again can be done using the spectral analysis. Well, health monitoring, diagnosis, yes, a different kind of electroencephalograms, electrocardiograms, and stuff like that. In data, specifically in digital, we quite often use that for compression purposes, say, for example, video codecs, yes, or JPEG format. All of that actually does calculate, transform as one of the steps, yes. So that's quite useful. Now, there are also some specific problems the moment we go away from theory and formulas in lecture and start to actually do some action with the real signal, like, capture some, for example, microphone data, yes, save this as file, load it in MATLAB, and try to analyze that audio file, yes. Now, there are specific problems that we will run into. Some of them are purely practical limitations, which we didn't even know about in theory, yes, and some of them are, well, kind of theoretical as well. So first of all, the problem is we do not know when that spectrum is actually observed. So let me try to kind of show you with this same picture here. For example, for this fragment of the signal, I will have one picture of spectrum, say, for example, something like that. Then I will have another fragment of the signal, which is going to have a different spectrum. Yet another fragment of signal will have a different spectrum as well. And here we have localization problem, because we now not only want to know the spectrum, but we also want to know when that spectrum in the signal actually happened, because the spectrum is going to change. If you were to take some radio, connect some spectrum analyzer, and see on the screen what happens to the spectrum, you will see that it constantly changes. It's not static picture, yes, it's actually dynamic, and hence now we speak not only about that the particular fragment of signal has the specific spectrum, but we also speak about what time duration that happens over. And obviously, the bigger is your fragment of signal, for example, here we can specifically say, okay, the spectrum corresponds to this short fragment, but what if I will now take instead the entire fragment of the signal? Will be so possible to be saying accurately where exactly this particular picture of spectrum is known? No, it's actually matching the entire interval, and as of such, we are now introducing some problem related to the resolution. Yes, so the resolution is basically allowing you to say in two domains. Yes, so basically on one axis we will have frequency. On one other axis we have time. And of course, ideally, we do want to say, have very accurate time and also very accurate frequency. Say in particular, for example, for the specific signal, we now say, okay, at the time moment 5.32 seconds, we have observed a spectral component frequency of, I don't know, let's say 111.3 Hertz. To be so accurate. However, the problem is that it's impossible to have them both. Yes? So you will kind of have to trade one for another, because you can actually say, okay, I will determine this time very accurately, but then you will simply say, okay, my frequency is somewhere here, which is not as accurately. Or you can specify frequency very accurately, but you will not be able to tell when exactly that happened. This is actually very similar to this Heisenberg principle in physics, where you have the elementary particles moving randomly, yes, and then you can evaluate two things for those particles. One is its position, where it is happening right now. Two, its impulse, yes, like what direction it's going to. And it turns out for this elementary particle, you cannot have both of them accurately, yes? Either you can know specifically that it's currently right here, so you can find it precisely, but then you have no idea where it's going to go next, because it's a random process, yes? Or you can kind of track its movement, but then there is no way for you to tell at this particular time moment right now where exactly it's going to be right now, because it's a random process, yes? So you kind of trade one versus another. That's called the Heisenberg principle in physics, yes? And it's very similar problem here with the resolution between frequency and time. So you can have either one or another. When I will show you something called a spectrogram, which we will also discuss what exactly that is and how to construct it, you will see that very clearly, yes? Another problem is called a spectral leakage. Yes, so spectral leakage is a problem when we actually cannot calculate the frequency component exactly, yes? So let's see, for example, discrete Fourier transform. Say, for the simplicity, I am not going to use power of 2, but just say 100 samples. Yes, so here we have 0. Here we have sampling frequency, f sampling. Well, for the sake of example, let's take some specific number. I don't know, let's say 20 or maybe like 40 kilohertz. Yes, so to have just some specific number. And then we know that you have, let's say, discrete Fourier transform with n equal 100. That means you take 100 of your data points and then calculate 100 of the spectral components. So that means you will calculate some spectrum. It doesn't matter what exactly it's going to look like. I will draw something like that, which is also going to have n of 100 of those samples. Now, with that in mind, we can actually find out what exact frequency values we will be observing. So if the entire range is 40 kilohertz and we split it into 100 pieces, yes, so that means we go with a step of 400 hertz. So this is 400, this is 800, this is 1200, 1600, and so on and so on. Now everything will be good if you will have in your signal actually those frequency components. But what if the frequency component your signal has will be actually 1000, which is not going to hit any of those points because you do not have enough of resolution. That's exactly resolution here, yes? You are having not enough of those samples. You need to have more samples to be able to find it more accurately, yes? So, for example, in this particular case, your spectrum can contain only information about 400s, 800s, 1000, 12, 200s, yes? But not about 1000. Thousands is in between 800 and 1200. So what is going to happen is this energy of that actual component is going to be kind of like smeared across the neighbors, yes? And instead of having one actual precise component, you will now have some kind of like area of the spectrum. So this is exactly leakage. Its energy is leaking towards its neighbors, yes, which do not exist, yes, because your real frequency is 1000, but in your spectrum you are going to see some value at 800, some value at 1200, even some value at 400, yes, because that energy of 1000 component was distributed between the neighbors. And that happened because you simply did not have accurate enough frequencies. So what that means, we could have avoided that if we said, okay, we will use not 100 but 200 of points. In that case, you would go with a step of 200, which would actually hit 1000 precisely, and that would not happen, yes? So again, that's another practical implementation. How do you know what number of n do you need if you have signal that's actually random, changing, and so on? The simple question is you do not. There is no way to know that. Yes, so we will have to deal with this somehow. So that is another practical aspect. Non-stationary signals, well, in a probability theory, we will have actually one of practical exercises to run some tests on data to determine is it stationary or not. But in the simple sense, we can say that stationary process, yes, stationary random process, stationary stochastic process, and so on, something like that, is the process for which we have statistical moments like average, constant, variance, constant, skewness, constant, and so forth. So these numbers are not changing over the entire duration of signal. Now, non-stationary process is going to look more like this, or perhaps somehow like this. Now your sigma square and mu is actually changing, yes? So now mu is kind of like a function of time, just like the sigma square is also a function of time, yes? So it's now variable parameter. We cannot say that the average of that signal is some number, because that's a question. What interval are we talking about? Are we talking about average over this interval, or are we talking about average over this interval, or maybe over this interval? Yes. So whichever interval you choose, the average is going to be different, actually by a lot. Yes, so that is called non-stationary process. And the thing is, majority of signals we are dealing in the real world are going to be non-stationary. Yes, and well, that's a little bit more complicated because in that case the spectrum also changes. The spectrum also is not constant. Yes, we cannot say that your signal has particularly this kind of spectrum. The spectrum is function of time as well. And of course there is also one more important thing called transient process. Yes, so transient process is something that happens like transition when system goes from state A into the state B. Yes, and in majority of real world applications, yes, so we can say, okay, we have some kind of a system. Which is now going from the state A into the state B. And in majority of real world systems, this transition cannot happen like this in one moment of time. It is actually going to take some time for this system to go from one stable state into another stable state. So, for example, we can discuss some electrical circuits, yes. Well, let's say, for example, we have inductor, we have resistor, we have capacitor, maybe some more resistor, and stuff like that. And then you have the battery here with a switch. Yes? And that is something you observe, for example, in motors when you start up some kind of motor. Yes? So what happens actually when you turn that switch on and we take, for example, voltage on this resistor. So I'm not going through specific calculations. I don't want it to be very accurate, but just the concept is that we consider this happening like this: 0 volts. Let's say here we have 5 volts of battery, yes, and 5 volts. That's what we think is happening, but that's not the actual reality. In reality, actually, we will have 0 volts, then some transition, and even so, this transition might take some time to stabilize. Yes, that is called transient process. Yes, that it's not happening like momentarily. There is some extra time for the system to be unstable in transition state from between state and A and B. It's like many kind of systems can work like that. Even like a person, say you are now finishing your bachelor, yes, then you want to continue your master's degree, let's say in some very prestigious, I don't know, United States university, then you send application. So you are now finished state A, so finished your studies here, but you are not yet in state B, so you are kind of like hanging up and waiting for the decisions. You are kind of in unstable state, yes, because depending on the answer, different things will happen. So that works for many kind of systems, yes, not just electronical circuits. It can be kind of described about people as well. So okay, those are problems that we are going to have to deal with, yes? And now let's try to at least start talking about how exactly we can solve at least some of those problems, yes? Because some of them are unsolvable, yes? Some of them are kind of like trade-off. You either choose one or you choose another one. Then you basically lose something else, yes? So, well, first of all, speaking about the problem of localization, like we don't know when exactly the event actually happens, that is so as long as we take this entire signal and calculate its spectrum over its overall duration without splitting it into fragments. So in that case, there is no way for you to tell that spectrum is kind of like, you know, changing or whatever. You simply calculate the average spectrum of the entire signal. Just like you can calculate average for any number sequence, you can also average out the signal itself, yes? And there is no way for you to tell that something is happening in that signal. Say, for example, we are particularly interested about this spike, yes? Yes, and in every spectrum, there is no way for you to get any reasonable information about that. So what we are going to do then is to say, okay, now we are going to split that signal into fragments. Fragment 1, fragment 2, fragment 3, And for each, then we calculate spectrum. In that case, your spectrum, every time you calculate and update it, is going to change. Yes? Now, there are, of course, multiple problems with that as well, because you can do so only a limited number of times. And the bigger fragment you want to have, the less of such fragments you will have, because I can easily split this into 100 very small fragments, but that might not be good enough for me to get detailed spectrum information. I will, however, know precisely, very accurately in time domain when that happens. But, as I said, spectrum is not going to be so accurate because we just don't have enough of signal data to actually get very accurate spectrum. Or I could take this entire fragment of signal and get very accurate average spectrum. But I will no longer be able to somehow tell how it changes over duration. So that's exactly this resolution problem, yes? Now, finally, there is one more thing, kind of like cheating stuff, yes? Nobody says you have to split this signal into fragments without overlapping. Like, well, maybe let me just take this snapshot to show it. So let me make some copies of that stuff here. So we can make splitting into fragments like this, obviously, fragment 1, fragment 2, fragment 3. But then we will have only 3 fragments. If we want to have more fragments, we have to make them shorter. Or we can actually overlap those fragments, say by half. Fragment 2, fragment 3, fragment 4, and we still have fragment 5 and maybe even fragment 6. Without actually changing the length of the fragment. True, we do reuse the same fragment of the signal multiple times, yes? But then again, we will have a good reason to do so, yes? So that's one more thing here, that you can actually split the signal into overlapping fragments, not necessarily have to be non-overlapping. Then each of those segments is being calculated as a spectrum with the FFT function that we know and used already, yeah? So nothing changes here. The particular algorithm to calculate spectrum is the same. It's more like of a concept, how we apply it to the dynamic and real-world signals, but the mathematical method is the same, nothing changed really there. So you split it into segments, yes? Then you use FFT for each of these segments, and then you get multiple spectrum pictures. So for example, here you can see spectrum 1, spectrum 2, spectrum 3, yes, how it actually varies a little bit. So spectrum 3 in this particular case, as you can see, is kind of like a combination between those two. So that is one of the examples, yes? Now, how do we then represent this spectrum on a picture? Yes, because if we take a video, that's nice. In the video you can show how it actually changes, yes, and so on. But how can we show all of those spectrums for the entire signal, considering that we split it into fragments in one single picture? Well, that is called a spectrogram, which we will discuss now. But before that, let's actually make note that the method which we discuss now is called short-time Fourier transform. So for short, STFT. Yes? When you actually don't use the entire signal, but split it into fragments, segments, and then apply method for each of them. Now it has its own benefits and its own weaknesses. First of all, the signal changes in time, but if it changes quite slowly, then we will actually capture enough of the details and get pretty good representation of the signal. Yes, that is particularly useful for working with music, which is slow signal kind of, yes, speech, electroencephalograms, which are basically like, I don't know, 5 hertz, 10 hertz, yes, so 5 oscillations per second and so on, which are considered like very slow processes. Now, again, short-term Fourier transform is coming to our aid when we not only want to know what is the spectrum, but we want to say that the spectrum is changing, and we want to know in particular at every time moment what exactly the spectrum was. Yes, so we have dynamic system with dynamic signal and changing spectrum. So short time Fourier transform actually allows you to split it into segments and tell that for this segment we have this spectrum, for this segment this spectrum, and so forth. Yes, like here, which allows you to show dynamics, and actually meaning that you can now see some events happening, like here, for example. Consider that this is one person speaking, another person speaking, both of them speaking at the same time. So you kind of can detect whether one of the people were speaking or both of them at the same time over the span of time duration. Yes, so this is kind of like detection. We will use that in practical exercise to detect any kind of faults for engine of car, yes, by analyzing audio data. Now, we also need to say here that we cannot avoid this resolution trade-off, like I said, accuracy for frequency or accuracy for time. You cannot have both, so you have to kind of trade one for another. You want better accuracy in time, you will have to deal with a worse accuracy in frequency, and vice versa. Of course, you kind of can try and get both of them medium, average, not so well, but again, usually we would still prefer some of those parameters, one of them, to be better, and we can afford to say, okay, then, well, time detection will not be so good, but at least I got good frequency resolution, yes? So here are two questions that we are interested in. First of all, we want to know if the frequency is actually accurate enough, because that is what the resolution of frequency is actually speaking about, yes? How many samples we can have, which determines how many signal samples you have. Yes, again, that's going all the way from here. Yes, say if you have, I don't know, those same 100 of samples, yes. So 100 of those samples in your signal, then your spectrum also will have to have 100 of samples. So the spectrum has the same number of points as your signal. Now, increasing the number of points in signal increases the time of this signal, yes? So you take longer segment or shorter segment. And the problem with that number, 100, is that in your spectrum, whenever you calculate that, yes, here you have 0, here you have sampling frequency, and the step at which you can discover different frequencies is going to be f sampling versus this 100. So that is where this fundamental limitation of resolution comes into play, yes? Because you want to have those frequencies with much smaller steps, yes? So you would prefer to use not 100 here, but 1 million maybe, yes, to get a very, very accurate frequency positions. But that would also mean that you would have to take not 100 of signal points, but 1 million of signal points. That's going to actually be this fragment of signal. And therefore, you will no longer be able to tell when exactly that spectrum was observed in those 1 million points. Yes, so you lose time resolution, but improve frequency resolution, and vice versa. If it's very important for you to actually detect the particular frequency as soon as possible, then you want to make this fragment very small, not 100, but 10, yes, for example. Unfortunately, though, that means also that you will have to deal with this frequency step of sampling versus 10. So if our sampling frequency was 40,000 hertz, yes, dividing by 10, that means that the step between two frequency components is going to be 4 kilohertz, yes, not 400 as before, not maybe 0.004 if we were to have 1 million samples, but in all, the detailization is going to be not so good there for spectrum, because you will only have 10 spectrum points. I mean, how accurate it can be, yes, because of the leakage that I discussed. But at the same time, in time domain, therefore, you will still precisely know, okay, that's the spectrum I know, but at least I know that it actually happened over this duration and I can track it very accurately in time. That's where this limitation actually goes from. Now, weaknesses, yes, is the same resolution trade-off. So if resolution trade-off is acceptable, then we can use it. If resolution trade-off is not really acceptable, well, this is not really the method to use, but the problem is that we don't have any other means anyway, yes? Well, almost, yes? Now, also, if the process is non-stationary, which is the majority of cases in the real-world application signals, then we kind of have to use maybe some other transform, for example, a wavelet transform, which we will discuss on one of the last lectures of this course, yes, and stuff like that. Now, there is also a problem when you need to have high frequency resolution for very low frequencies, yes? For example, how to understand that? When you have some spectrum, yes, and sampling frequency, and now what you want to do is to study some very, very super slow processes that happens once over the year, or maybe once in the hundreds of years, like, you know, these seismic activities, like tectonic plates of the planet moving very, very slowly, yes, literally by a fraction of centimeter per year. And that produces the spectral components of super low frequencies like, I don't know, just for sake of example, 0.000000001 hertz, yes? And that is a problem, because to be able to determine whether it's 0.0001 or 0.0002, you need to have a super high resolution, yes? That means you have to have like millions of points here. And whether you are interested just about this fragment, that doesn't matter. You still will have to go with the same resolution all the way up until the sampling frequency, whichever that is, yes? So that puts you into the position that you have to have very long measurements, yes? You have to have measured this signal for years to get this resolution, yes? That is a problem. Yes, that's why those radio astronauts, yes, geologists do need so much data and take that long measurements. Another issue is, of course, computation efficiency, yes, because now we no longer have this fast Fourier transform and that's done, but we have to split into segments. Now, as we'll discuss, we actually cannot take those segments as they are. We have to process them a little bit to make them more suitable, because the majority of the problem is, well, if you look closer here, you will notice that it's not actually cutting out this fragment of signal as it is, but instead, for some reason, it became 0 at the beginning and 0 at the end. So we kind of like, you know, shape it a little bit by reducing the edges of the signal. And there is a good reason to do so, yes, I will demonstrate it also, and we do that in practical exercise as well. But that also is why actually overlapping comes into play, because here you can see that you kind of nullified this section of the signal and you don't have its information anymore, but in the next segment there it goes back here and so forth, yes? And you need to realize that those are computations that you have to do. Yes, you take a segment, you apply some window to that segment, then you calculate spectrum, then you take next segment and so forth. That's much more computational intensive than just fast Fourier transform. Okay, now let's try to represent the visualization of that procedure of actually trying to localize spectral components over time. This is called a spectrogram, and it's kind of like very similar to music notes. Yes, like you know that you can visualize some music compositions with different of those notes. Yes, and actually, if we record that by, well, say, for example, some musician sees this picture, yes, sits over to the piano and plays some music for you. And we record that music with our microphone and then get the spectrum of that. So in the spectrum, you will actually see that every time the person presses the key of the piano, it produces specific frequency component, yes, the note. And each of those notes is actually like really showing like those levels, yes, like so. And each of these keys is also having different duration, yes, but at the same time there is some physical limit and the person can only press those keys just so fast as he can, yes? It cannot press it like with the microseconds, yes? Because that's physically impossible, yes? So there is some time limit for us that we analyze this. And then we see that, for example, for this time duration, it sounds the key, I don't know, notes, sorry, which one is that particular one note. Then next note is a little bit longer, next note is a little bit shorter, and so forth. And that's how we represent this music. And on the x-axis, you can see time, that shows how this changes in dynamics in time. As time goes forward, you can see that notes change. And on the vertical axis, you can see the frequency, the note that we are playing right now. That picture is actually a spectrogram which shows you how spectrum of signal changes over the time with one single picture without having to record the video fragment, yes, and somehow send it and do stuff like that. Now, that's actually the same procedure that we can apply for any kind of signal, not necessarily just music signal. So here, for example, you can see some signal, yes, signal of different frequencies, and then I take 3 fragments of that signal. Fragment 1, and calculate spectrum for that fragment. Fragment 2, calculate spectrum for that fragment. Fragment 3, calculate spectrum for that fragment. Yes? So as simple as that. I simply cut off a piece of the signal, get FFT, get the spectrum. Yes? Well, we'll speak about extra processing as we go, but the concept is the same. Now, there is one more thing I want to introduce here before we go further, is that now we are actually going to show the intensity of the spectrum with a color, meaning that low intensity will be dark blue, super high intensity will be red, and something in the middle will be yellow. So the stronger is the spectral component, the lighter color becomes. We color map the value of the spectrum. Yes? That will be super useful for us later on. So what happens now is we split this signal into those fragments, overlap them, go through the entire signal, calculate, I don't know, 1,000, 2,000 of those segments and their spectrums, and put them into one picture here, and get the spectrogram. So basically what you can see in this spectrogram here is those spectrums that we discussed. Here, for example, this part goes particularly here, and you can even see with color how it goes from the lower values, then at around specific frequency close to 100, it maxes out, yes, with the yellow color here, here, and then it again decreases, and then it's blue. The second fragment is somewhere around here, yes, around 300 Hertz, which is here, yes, and the last one is around here. So this picture is called a spectrogram, and it shows how frequency of the signal changes over time. Yes? And so far maybe you didn't notice it, but actually I have constructed this signal intentionally so that here, over this fragment, yes, it's difficult to see maybe, let me just cut it out. Well, actually, let me cut out this entire thing here. So over this fragment here, our spectrum is frequency is actually constantly increasing. So I started with lower frequency, and with every time moment the frequency becomes larger, faster, 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 and faster. So it constantly increases, and that's what we can see in the spectrogram here in this line. Yes, so you can see that the frequency actually increases linearly. Yes, so that's exactly what I wanted to. And for the second half of the signal here, I said the frequency is constant, it's not changing anymore. And that's exactly what you can see here. The frequency is constant. Yes? So this picture shows the dynamics. Now, there are several things about this picture that we can control. First of all, you can see that we actually have this kind of like sampled, yes, kind of like a discrete process, and there are several limiting factors for us here, because from this perspective, if we simply take this yellow line, we can see that this yellow line is quite thick. Yes, so that means you cannot read the frequency very accurately. It's some range, yes, minimum and maximum, and real number is somewhere within. At the same time, also, you cannot really track how fast that changes. Yes, so this is the let's maybe use some different color, no, this one. This is the window size of which, and you are limited to actually having to deal with that over this time duration, frequency is constant, yes? Because that's exactly what we can see. You can see kind of like steps here, one step, another step, and for each step the frequency doesn't change. But in reality, of course, the signal frequency increases continuously as continuous line, so it doesn't work like step size, yes? Like, I don't know. Let's write some examples, yes? For example, here, oh, sorry. Let's use smaller font here. Say, for example, here we have 75 Hertz at the beginning, yes? Then the next step is 85 Hertz. And that is how limited your system is. It cannot find 76, it cannot find 77, 78, 80, 81, and so forth. It deals with the steps of 10 Hertz, yes? But in reality, this frequency all the time was constantly increasing with 0.001 Hertz at every 1 microsecond, for example, yes? So the real picture is, so the real frequency change is more like looking like this line, whereas the histogram, or spectrogram, sorry, actually gets this as kind of steps instead. So this is limited accuracy that we have to deal with. Of course, we could make this step shorter, but as I said, that would lead to the fact that you will no longer be able to precisely tell the frequency. Yes, so that's what I'm going to do now, is to show you, okay, what happens if we now make this step smaller to get faster tracking of the frequency? Well, as I said, from the Heisenberg uncertainty principle, that means that the frequency itself is going to become less accurate. Meaning that, yes, you will be able to track the frequency faster, but the frequency itself will be not so accurate. Yes, it will change, obviously, yes, but you will not be able to find it so accurately. And vice versa. If you want to have more accurate frequency, yes, to narrow down this range, which you can see in color transition from blue to green and yellow, yes, then you have to make longer steps. And that's exactly what is the resolution problem, yes? So here you can see two spectrograms, one spectrogram and another spectrogram. And what they different with is this resolution, yes? So on the picture one, we have better time resolution, seeing when that actually happens, yes? So here or here. But the frequency itself is not so accurate. Yes, we cannot say particularly that this is some particular precise frequency. It's some kind of range that your frequency is within. Here, now you can see that the fragment became longer than it was. And even more so, it's not only longer, it's also kind of transitioning from blue all the way up to the red line, yes? So it's not like on-off as before, so like it was here on. Well, let me actually get those two pictures, one beneath another, and I will be able to show it much better then. Yes? So picture 1 and the picture 2. Like this, yes? So now you can see that the actual starting moments here were here and here, and those starting moments are now kind of like a little bit smeared for the picture below. That means your time resolution is now worse. You can no longer say where exactly is the beginning of this frequency, yes? Whether it began here, or here, or here, or here, it actually is kind of like distributed along this range. But at the same time, the frequency itself is much, much more accurate, yes? So here you were saying, my frequency is somewhere around here, yes? Now your frequency is actually pinpointed very, very accurately. So this is the resolution trade-off I'm speaking about. You can have either very accurate frequency, but then you cannot really tell when that happens. Or you can have very accurate time tracking, but then your frequency will be only told approximately. Yes, that's the problem of the resolution and uncertainty principle of Heisenberg. Yes, so basically that's what is shown in this picture. And here we speak about it, that actually there is a formula that ties them together and says that your frequency resolution and time resolution is kind of like a constant. Yes, so that means you have, in a simple manner speaking, yes, maybe let's use some basic numbers instead. You have some number A, well, understand why it's not changing. Okay. So, okay. So you have some number A, some number B, and basically A is the time resolution, B is the frequency resolution. And Heisenberg principle says that A multiplied by B can only be 1, nothing more. So if you want to have better time resolution, that means A will be higher, 100, then you have to have worse frequency resolution for them to add up, multiply up together into the 1. That's the constant limitation. And another problem even that is that it's very difficult for us to trade one for another, actually, yes? So wavelet transform, for example, is a little bit better in this sense, so we'll study that definitely as well. But at the end of the day, we kind of still can choose one number, but specifically the problem is that when you choose one number, the second one is chosen for you automatically. So you don't kind of have the freedom to choose both of them. Once you choose one, another is chosen for you. Yes. In wavelet transform, you have a little bit more freedom in choice and being able to redistribute your desires. So okay, here now we have high time resolution and low frequency resolution, meaning that I am able to track pretty accurately how the frequency changes, of course with some particular discrete step. but the frequency itself is in the range, is in the interval. It's not precisely, let's say, 75.3 hertz. Yes, it's some approximate range value where it is. Yes. Now, if I change the resolution, yes, and get higher frequency resolution but lower time resolution, yes, you can actually see, well, it's difficult to see on the projector, yes, but when you look on these slides, or maybe let me try to turn down some of the lights, yes? Yeah, I think that's better. You can see how it's kind of like lined up, yes? Because that is the step of the frequency we are speaking about, yes? How accurately we can estimate the frequency. Now, this colored interval is the matter of leakage, yes? We'll deal with leakage by using something called window function. But right now, fundamental limiting factor is that you can only tell difference between frequency with this particular step. For example, in this case, let's say this is 5 hertz. So you can have 0 hertz, 5, 10, 20, 15, 20, and so forth. You can go only with a step of 5 hertz, and those are the lines you can see here. Now, if we increase the frequency resolution, that doesn't necessarily say you will solve the leakage problem itself, yes, without windowing, but what this picture actually shows is that now this transition is much more smooth. Now we go with not 5 hertz step, with 1 hertz step. And therefore this gradient is also much smoother. Now the problem with this part here, before this here, is that the frequency actually is not constant in this duration. This is the non-stationary process. For example, at the beginning frequency was, I don't know, 70 hertz, at the end frequency was 120 hertz, yes? But you calculate that entire fragment and get the average spectrum. So that means that there is every frequency in this range on average, but at much lower rate. So how this picture should have looked like in reality, yes? Let me try to get this. In reality, then we should have this bright red color going like this line. Sorry. Well, actually, I can use mouse for this like that. Like so. But before your fragment of the signal is actually limited with this time duration, then as you can see, within that time duration, your frequency changes all the way from here up to here. And the frequency itself is, sorry, like the linear function here. Yes? So that means that your fast Fourier transform is going to calculate the average of that frequency for every component, which in turn is going to end up with much lower level, evenly distributed among the entire range. And the green means that its amplitude size value is lower than red. Yes, so that's exactly what you see here. It was smeared, leaked across this frequency range. So here we have actually very good frequency resolution because we can see it here. When the frequency actually was not changing, we get this picture much more accurate than before. So before, it was looking like this. Yes, you can see that this line now is actually much thicker. Now, after we increased frequency resolution, here we actually see it much better. Yes, much more accurately. But the problem is with the actual fact that the frequency itself is not constant in the other fragment of signal. Here, for example, you can see that this also brings up all the way up to the green tone here. What that means is that the energy of your two signal frequencies is now distributed along the entire spectrum. It's this smeared licht, yes? And that's very interesting to notice here, because that is exactly where transition happens, yes? In my case here, yes, I did this transition rapidly, so my frequency was, so maybe again, let me copy that one. Put it below, because this precisely corresponds to this spectrogram above. Yes, my frequency here was increasing all the way in this range, and then I said it's constant. So that's how perfect spectrogram should have looked like. Yes, but because of the leakage and having to calculate the average of these entire intervals, so like here average and here average and here average, and also here, yes, you can see that this time intervals is so long that it actually captured the fragment of the previous increase here and the new constant value. Yes, because of that, actually, yes, we have both of them in this time segment, and because we do not have good enough leakage suppression, we kind of cannot tell them accurately. So you can kind of see both of them at the same time, but not so, how you would say, not so contrastly. Yes, like here, for example, here you can see this is dark color, and this is very bright. Here it's also bright, here it's not so bright, but the entire background is also not dark, yes? That means the entire energy of this fragment has been distributed along the entire spectrum, yes? So it averaged out, yes? And because it had both this frequency and this frequency, everything was averaged out, and that's what we see here. That's particularly why this picture looks like that. Now here we try to do something like balanced, yes? So we kind of get one good enough and another good enough, yes? So this is our attempt to balance things out, which may or may not be so successful, yes? Because here actually we did have quite good time resolution but very bad frequency resolution. Here we had very good frequency resolution. You can see how again, on projector it's difficult to see, but here, particularly these green shades are actually very, very smooth transitions, yes? Not like these discrete jumpy steps, but actually nice smooth gradient with the stones growing one into another. Yes, that's because you have high and very accurate frequency step. Here it's kind of between the picture 1 and picture 2. Okay. Why that happens and what exactly is this leakage? So this happens whenever we try to capture a harmonic component, because as you remember, your signal consists of harmonic components, sine waves and cosine waves, yes, of different frequencies with different kind of like strength or contribution or amplitude, yes? And we do here cut the signal into fragments, yes? Like so, we cut the signal into fragments, and the question is, how do you cut it? What is going to happen to the harmonic you are cutting? Because you can cut harmonic at different places, yes? For example, here, yes? You can see that we have this harmonic, and we cut off it particularly in this place. But if we do, then trying to repeat this thing is not going to produce harmonic. So what exactly happens here? Let me just show you what happens here to explain better the problem. So new. That is precisely the problem of cutting the signal into fragments, yes? So as you can see here, we have a harmonic signal, sine wave, smooth and nice, yes? And we decided to cut fragment of this harmonic wave at this position, like so, yes? Okay, we cut it out, so I'm going to also cut it out and have it as a fragment. Now, as we discussed, discrete Fourier transform actually mathematically assumes that this signal is repeated before and after infinitely. So that means that fast Fourier transform actually calculates this signal like so. And the problem is it is no longer a harmonic signal. It is no longer a smooth sinusoid. Although originally it was, it's just that we cut it so unsuccessfully that during the fast Fourier transform calculation, this becomes something else. That is how fast Fourier transform works. It has to say that your signal will be repeated over and over. So that means we should have cut it slightly differently to achieve the desired effect. So if I were instead to cut it off like this, then everything would be fine. Well, some overlapping here, but more or less you get the idea. So it's super important at which point you cut off that signal. And as you imagine, nobody is going to sit and study that signal, especially considering that your signal is not going to be one harmonic, but maybe thousands or millions of different harmonics. So whether you like it or not, some of the harmonics will have to be cut off improperly. Yes? And if we calculate the spectrums of those two signals, then you will see that actually it's a different thing. Yes? So that is the problem of leakage, basically, yes? Because we kind of have to cut off the signal. I think there is nice video, not video, but GIF animation here showing you this procedure. Window function. So some spectrograms, the same stuff we've had. Some programs, yes, which we will discuss as well. I think we will use or not. I don't remember this particular one, but we will have our own. But what's important here is this animation, which shows you how our window moves along the signal. And depending on the position, you can see that this periodic function kind of changes a little bit, yes? So you cut off at the beginning or at the end. And you get full period either way. Yes? And if we look at that in more smooth notation, yes, you will see how it goes from the periodical one into non-periodical one. Yes? So basically, we have a problem of this here, yes, this one which is to the right, being completely not like a harmonic signal, like something completely different. And only because of how your moving window acts, yes, over different harmonics. And again, let me remind you that your signal consists not of one harmonic. So you cannot simply take your signal, analyze it, and say, okay, I'm going to cut it off like that. It has multiple harmonics of different frequency. So that means, whether you like it or not, there will be some harmonics that will be cut off properly and some that will not be properly, yes? That produces this leakage, yes? So here, let's try to open this video link as well. Wait. I want to, not full screen, I want to have it theater mode, yes, like this. Okay, so here we can also see how we can use our windowing to help us, yes, so that will be another video. Let me actually open this right away so that advertisements can also play in that time. Here we do not have any adds. Here we have add skip. No thanks. Yes. So what happens here is basically that problem of cutting down signal not really in the best possible way. Yes. That's producing those jumps. Yes. And as a result, when you calculate the spectrum, yes, we already discussed that. For example, here the A, sine wave, in ideal spectrum is going to have one discrete sample, like at this particular frequency, one very accurate value. For the rectangular shaped signal, we considered, okay, it consists of multiple harmonic waves, so every of those harmonic waves is going to produce its spectral component at different frequencies of different amplitude. And together, they form the square wave. Now, interesting to know that this transition, like fading harmonic signal in the frequency domain, is now actually going to have this leakage we discussed, because originally it was the same harmonic wave as here. Now it's leaking because the actual spectrum of this signal has more harmonics than just one, and you can see it here. And at the same time, in time domain, a single short, like burst, like impulse, has infinite spectrum. Yes, that's how we describe the noise. Okay, let me check whether there was something interesting else. Yes. So here, what we should do instead is move this window a little bit. Yes. Wait, no. So what we should do is to move this signal, but that's not practical. As I said, we cannot really solve all our problems with that, because there will always be some frequency that is going to be cut off like that. So the question is, what then do we do? We do apply a window function to our signal fragment. So what exactly that is, you can see here. Then up there is your signal fragment, which we have, which does have this problem we discussed. Then we use a window function which has 0 at the beginning and 0 at the end, and we multiply it with our signal fragment. So your signal fragment now will have to start at 0 and end at 0. And that's exactly what we need to solve the problem, because as I said, fast Fourier transform is going to replicate this signal for you, and if it starts and ends at 0, that's not going to be a problem. See? Here, Yes. Here, it smoothly continues without jumps. It's no longer a sinusoid, true, but at least it has that sinusoid in its spectrum, and it also does not have those edge effects. Yes? When you had this before, like this. So that jump, that transition from this 0 to this point is actually very bad, because that's going to distort your spectrum a lot. And here, by using that window function, we actually solve that. Yes? But we kind of created a new problem instead, yes, of the leakage, in a sense, yes. But, well, okay, so here we can see 3 pictures, yes? So the leftmost picture is the theoretical spectrum of harmonic wave. So you have harmonic wave, and theoretical spectrum is very, very narrow, very, very short pulse of the specific frequency f. Now, if you cut it off incorrectly and calculate fast Fourier transform, then instead of this narrow spectral component, you are going to get this entire thing here. That's basically going to have its own energy distributed along much wider range. Applying the window is now creating not a harmonic signal, as you can see, but something like these poles, radio poles or something like that, yes, which doesn't have so sharp and accurate spectrum, but the leakage is much, much less than it was in the middle. Yes, so you can clearly see that this picture here is much better than this. So actually windowing did help a lot to solve this kind of a problem. Now, well, maybe let's just take a look past how different kinds of window are going to be affecting the spectrogram of this signal. So the signal is here, yes, the same signal I was using before. Now I'm going to use different kinds of window functions, starting with rectangular window. Rectangular window means that I have some signal. Well, I'll display some signal, random one, yes. And I cut this into fragments by using the window of the rectangular shape, like so. So basically, without smoothing any edges, like the signal way it is, I take it straight away, cutting off edges, and that's it. So that is the spectrogram you are going to get for this window. And this is the spectrum of the window function itself. Well, rectangular poles having sin x versus x type function, not surprise, yes? Now we use Hamming window instead, yes, and you can clearly see already some improvement, yes, because here you had too much of the leakage, and the leakage in that picture is basically showing the background color, yes. Here you can clearly see the background color is somewhere even like yellow, green, yellow, and so forth, and here background color is much darker, yes, meaning that energy actually is calculating more accurately for the signal itself rather than leaked in the non-existing frequencies. So the Hamming window is different. The Hamming window is looking like this. Yes, so it starts at almost zero and ends at almost zero by reducing those edge effects. There is also another window called Han window, which starts and ends precisely at zero. Yes, so Hamming has a little bit non-zero contribution to the edges, and Han has zero contribution. Yes. Again, we'll speak about those windows, their particular formulas, shapes, and so on in the next lectures. But right now, I just wanted to show you how this actually changes a spectrogram a lot. Yes, because we had this rectangular window, this is Hamming window, this is Han window, and also at the same time observe how we kind of like lose some frequency resolution here as well. Yes, because here it was more accurate, but background was lighter. Here is now a little bit more smeared, but background is darker. Now there is also Blackman, which is something in the middle between this one and this one, yes. And of course the Bartlett one, which is actually the triangular window, which also starts at zero, ends at zero, and kind of deals with this edge effect, yes? So here you can see some more spectrograms when I used as an input signal just a harmonic wave, yes? At the specific frequency. No, wait, sorry. This is the spectrogram of the window. Well, we'll speak of that maybe next time, yes, but for today, I think we actually are done, yes. So again, more details about windows, particular strengths and weaknesses next time, yes, or maybe in some practical exercise today, some of them. But then about periodograms and stuff like that, again, we will discuss further, yes. Okay, that means that for today we discussed the practical short-time Fourier transform, the spectrograms, and a little bit about windows. That means we are ready to go to computer class, and there you will have to take the electroencephalogram signals of brain activity in different sensors and points, yes, and get those spectrograms for that signal. Yes, I will actually show you how to do that. That's not too difficult. But hopefully it will also be something interesting, because there you will have opportunity to work with real data, yes, and then you will see something. Okay, that's it for today. Thank you for your attention. If you have any questions, don't hesitate to ask. But if not, then, well, hopefully they will come around when you will do practical exercises.